Margin of error versus sample size. We're going to learn about the following here. Firstly, to understand that in order to achieve the same margin of error at a high confidence level, so at let's say 99% for example, as you would in a lower confidence interval like 95%, we're going to need a much larger sample size. So the more confident you are, the larger the sample size you need, because of what we saw in the last video, because of the increased confidence interval means an increased margin of error. And secondly, we're going to learn that given a margin of error, we will do some calculations for a required sample size n. Okay. One way we can study this idea is to look at the formula for margin of error, and let's say we increase n and everything else is fixed. As we increase n, what's going to happen here? We increase n. Well, this fraction, if you want to call that, this operation in the brackets anyway, will, as we increase n, it will decrease. Okay, so the quotient in there will decrease, which means that the subject under the square root, whatever that is, okay, some amount, that will decline as well. And the rest of it is multiplied by the quantile z. It will also go down. So the entire expression e will go down. So in other words, this means as n is increased, the margin of error is decreased. So in this GeoGebra app we see here with the author written there, let's have a look at the same phenomenon. So for some population proportion and some sample proportion, if we look at changing some of the parameters here, and for a certain confidence interval, this one's 95, what happens if we increase the sample size? Okay, what happens to the margin of error? Okay, so we'll start at the lowest possible amount there, and we can see a few things happening as we slowly increase the sample size. The margin of error is dropping, which is what we said a moment ago. So we can get that the margin of error on a certain confidence level down to what it would be at a lower confidence level by increasing the sample size. Okay, and you can see that the confidence level has to have a consistent area. Okay, confidence interval itself is getting narrower as such. You'd see that in red, but the area under the curve has to be the same. That's the confidence level, like we said in the previous video. So the only way is up and in, in and up, and so that's reducing that confidence interval down, and therefore, as you know from the previous video, that means the margin of error directly related to that is going down. Okay, so sample size up, margin of error down, and vice versa. Okay. We saw this GeoGebra applet too in the previous video from this author. We can see if we turn the sample size right down to a low setting there, 10, a fixed population proportion at a certain confidence level, we can see the same thing happening. If we increase the sample size, so increasing the sample size, the margin of error gets less and less. And remember, the margin of error on this, whether it's a green interval or a red interval, doesn't matter. The margin of error is from one side to the other, with the sample proportion in blue in the middle there. Okay, so from the previous video we've seen this diagram. The red means that the interval did not cross the true population parameter, the true population proportion. Okay, so as we increase the sample size, we get better results in terms of a a lower margin of error. Okay, so the confidence interval starts to narrow up because the margin of error is reducing. So that's the first learning goal covered. The second learning goal being addressed now is we're going to look at calculating required values for n. What sample size do we need given a certain margin of error, or if we're chasing a certain margin of error? So first one, consider the proportion of primary school children, P, who use social media, and if we originally select a random sample of 200 children, so originally it was, call it N1, 200, and find the sample proportion P. Let's say it's 0.7. Okay, we did a sample. What sample size N is required to achieve a margin of error with those things held constant, like 0.7, in a 99% confidence interval for P? Okay, so we're going to change, N is going to change. Okay, so what will the new N be? Alright, so we've got a margin of error, so the formula is written down. So E equals the quantile Z times what's essentially a standard deviation, P times its complement, P hat that is. Okay, and because it's 99%, it's 2.58 is the quantile, and we've got N is the unknown, and we've got P times its complement, so that's 0.7 times 0.3, and the margin of error is 2%, so that's 0.02, so write it as a decimal, and then we need to do some rearranging. Okay, so we've got to get the 0.02, divide it by 2.58 firstly, then we've got to square both sides, then we've got to take the reciprocal of both sides, which is the same as raising something to the power -1. You can rearrange this in any way you want to, and then we've taken the reciprocal of both sides, and then we must times by 0.7 by 0.3. You could use different steps if you want to, just don't break algebra in the process. So I get 3494.61. Now we can't settle for 3494, we have to take it up to the next whole number, otherwise it won't be quite enough. So 3495 would be the sample size. Lastly, determine the sample size required to achieve a margin of error of 2% in a 95% confidence interval for the proportion of primary school children who use social media. Now you'll notice that everything's the same as it was in the previous question, except the confidence interval. Okay, 95% confidence level. So we should be able to anticipate our answer now. If we have a margin of error at lower confidence, we don't need as big of a sample proportion, or sample size, sorry, not sample proportion. The sample size need not be as big. So with that in mind, we have our quantile 1.96. Oops, I've done it again. That should be P hat there. So the sample proportion is 0.7 and its complement is 0.3 like last time. N is what we're trying to find. And again, 2% margin of error is 0.02. So we need to solve that. Now I'm going to use some different algebraic steps because this might suit you more. So we've got 0.02 divided by 1.96 is the square root of 0.7 times 0.3 over n. Then we square both sides. Okay, That's 0.21 over n. So with a bit of help from our calculator, okay, so that very small number there on the left equals 0.21 over n. So rearranging, crunching that, I get 2016.84. So for the reasons we mentioned just above, we need a sample size of 2017 for it to cut it. Okay, so sample size required is 2017.